Have you ever stopped to think about your workout gear? You know, how it's so soft but also super strong? Or what about those cleaning cloths that seem to soak up everything? Well, it all comes down to this incredible process called fiber spinning. Today, we're going to pull back the curtain and see how simple little plastic pellets get transformed into these amazing high-performance fabrics. Let's dive in. So, this is the big question, right? How do we get from a pile of basic plastic pellets to the kind of advanced fabrics we rely on every single day? It's a journey that's packed with some seriously cool chemistry and engineering, turning something pretty ordinary into something, well, extraordinary. So here's how we're going to break it all down. First up, we'll get a handle on what fiber spinning even is. Then we'll look at how you take a solid polymer and turn it into a liquid. From there, we'll check out the spinning machine itself. Then comes a really crucial part, drawing, which is the secret to making fiber strong. And we'll wrap up by looking at some of the incredible innovations this tech has made possible. All right, let's jump into our first section. So what is fiber spinning when you get right down to it? In the simplest terms, it's the core process of converting a raw polymer material into a long, continuous fiber. That's it. You can really think of this as a two-part deal. First, you have to actually create the polymer. That happens through a chemical process called polymerization, where you link up a bunch of small molecules into these super long chains. But what we're really focusing on today is that second step, taking that raw polymer and physically changing it into the filaments that become our usable fiber. So how in the world do you take a solid thing like a plastic pellet and get it ready to be shaped into something incredibly thin? I mean, we're talking way thinner than a human hair. Well, the very first step is you have to make it a liquid. You just can't shape a solid into a tiny filament until you make it flow. And there are basically two main ways to do this. For polymers like polyester or nylon, you can just melt them down. This is called melt spinning. It's the most popular method because it's simple, cheap, and you don't need any messy solvents. But for other polymers that would just burn up if you tried to melt them, you have to dissolve them in a solvent instead. That's called solution spinning. For the rest of our chat, we're going to stick with melt spinning. Okay, so our polymer is now a nice, flowy liquid. It's ready for the main event. So how does the machine actually pull off this transformation? Let's take a little walk down a simplified melt spinning line and see how all the pieces fit together. It all kicks off with the feed and melt stage. Those solid polymer chips get fed into a machine called an extruder. You can think of it like a huge heated screw that melts and mixes the polymer until it's a perfectly consistent, thick liquid, kind of like honey. Next, that molten polymer gets forced under a ton of pressure through something called a spinneret. Honestly, just picture a high-tech shower head with hundreds of teeny tiny, perfectly engineered holes. As the liquid streams, or filaments, come out, they're instantly hit with a controlled flow of cool air that solidifies them. This is called quenching. And finally, all these brand new solid filaments are gathered up together and wound onto big spools, or bobbins, at ridiculously high speeds. But hold on, we're not done yet. Not even close. In fact, those filaments coming right off the winder, they aren't actually strong enough to be used for much of anything. Their real power gets unlocked in this next critical step. This is where the real magic happens, turning a weak little strand into a seriously strong fiber. So here's the problem. Right now, these freshly spun fibers are surprisingly weak, almost brittle. If you could zoom into the molecular level, you'd see that all those long polymer chains are just a jumbled, disorganized mess, pointing every which way. Think of it like a plate of cooked spaghetti. This random, tangled structure is called an amorphous state, and it just doesn't have the strength we need for a high-performance fabric. And what's really cool is that the strengthening process actually begins right back at the spinning stage. This chart shows how the speed of that wind-up process has a massive effect on the fiber's internal structure. At slow speeds, you get what's called low-oriented yarn, or LOY. It's super amorphous. But as you really crank up that speed to thousands of meters a minute, you start to get partially oriented yarn, or POY. At that speed, the process itself starts to pull those molecules into some alignment, which makes the yarn stable enough to be stored before it goes to the final strengthening step. And this brings us to the absolute game changer for building strength: drawing. Drawing is just a fancy word for mechanical stretching. The yarn gets pulled between two sets of rollers, where the second set spins way faster than the first. This stretching physically forces those tangled, messy polymer chains to straighten out and line up, parallel to each other, all along the length of the fiber. This new, organized, tightly packed arrangement you see on the right is called a crystalline structure. And that transformation from molecular chaos to molecular order is the absolute secret to making a fiber strong. Okay, so now that we've got the fundamentals of spinning and, most importantly, drawing down, let's see what this incredible process of molecular engineering can actually create. We're going to look at one of the most famous innovations out there. And here it is, the microfiber. This is the perfect example of what happens when you perfect the spinning process. A microfiber is a synthetic fiber that is unbelievably fine. The technical measurement is less than 1 denier, which is a unit of fiber density. To give you some perspective, a single strand of silk is about 1 denier. A microfiber is even finer than that. We're talking about 100 times finer than a single human hair. Making something that delicate requires absolute precision at every single step we just talked about. And because of that amazing engineered structure, microfibers have some incredible properties. They're extremely soft and light, but they're also really strong and durable, thanks to that molecular alignment. Because all those individual fibers are so fine, they create a huge surface area, which makes them super absorbent. They can hold up to 7 times their own weight in water. That's exactly why those cleaning cloths work like magic. They're also great insulators, trapping air to protect you from wind and rain, which makes them perfect for performance apparel. And this quote just nails it, doesn't it? Performance with beauty. It's not just about making a material that's technically strong or functional. It's about combining that high-level performance with a material that feels soft, luxurious, and beautiful. And that's exactly why microfibers have become so popular in so many different areas. So we've gone on the whole journey, from a simple polymer pellet all the way to a high-tech material. We saw how it's melted, pushed through a spinneret, and solidified. But most importantly, we saw how the drawing process transforms it from that weak, random, amorphous state into a strong, aligned, crystalline one. The level of engineering here is just incredible. And it leaves us with a really exciting question to think about. Now that we can literally design and build fibers at the molecular level, what will the next generation of materials be able to do?